In this video, we're going to look at the universal motor. The universal motor is really the only motor that is typically used in both DC and AC applications. If we look at the winding structure and connections, you'll see why. Initially, we see the armature, which is the rotating part of the machine. We see our brushes and commutator, and then the connection to the armature or the rotating winding. We have a series winding here, so this is a series connected motor, and a compensating winding. If we go back to the DC machine, our traditional DC machine, we see the same type of structure on the rotor winding, or our armature. The brushes, the commutator, connections to the rotating armature winding, and then we have a series winding and a shunt winding. The potentiometer over here is for controlling the shunt winding current. In our initial work with this motor, we connected the shunt winding and did not use the series winding. But you can use either winding by themselves or even in combination as a compound motor. But the point is that the series winding on the DC machine can be similar to the series winding on the universal motor. So we'll take a look at the motors themselves and then see how they differ and how they are similar. So this is the DC machine that we have run data on. We see the brushes. We see the commutator down inside, and this is the brush positioning mechanism. We come over to the universal motor, and we see pretty much the same identical setup. The brushes, the brush positioning mechanism, and the commutator down inside the motor. So that's a view from the commutator side. Now we'll look at the winding side. This is the winding end of the motor, at least it's more exposed. What we see is the commutator armature system rotating in the middle. That's our armature winding. On the outside is the stator winding, which in this case is going to be the series connected, and there's also the compensating winding is in there also. On the DC motor, you'll notice there you can definitely see that this is a 4-pole motor. So there are 2 fields produced by 2 sets of poles. This is typical because it fills in the area to make a more efficient motor winding. But the rotating winding, the armature, looks identical to the AC universal motor. So we're going to set this up. We're going to take some data on the universal motor, and then I'll do a quick demo to show that the series motor can also be done on the DC motor. So the wiring of the universal motor is pretty straightforward. I've got it set up for DC right now. I'll switch to AC. So I come off the variable DC, I pass through the winding, pass through the series connection, and then I return to, in this case, the negative. Energize the unit, and it spins up, right? Series motors run pretty fast at low torque levels, and of course there's nothing connected, so it's very no torque, and so it's going to be a much higher speed. There's some torque through the bearings, but that's it. Okay, we'll switch over to AC and we'll see it operate. So I'm switching over to AC, so I'll use the variable supply again. Now we turned counterclockwise in that case, and again we switch counterclockwise. And so the unit runs up to speed. You can hear it speed up quite a bit. So I'll turn it down there, and that's how the universal motor runs. One thing I didn't show was how to switch directions on this motor. Right. Traditionally, a DC motor, all you need to do is reverse the polarity. And it'll change directions. So I'll switch the polarity on the AC, and you'll see, gotta have it on. Now you'll notice there that the motor spun the same direction, counterclockwise. So this is one of the challenges on AC motors, is switching their direction. Now we can switch the direction by switching the field in most cases. But look what happens. In this case, I switched the direction of that series field, and so since I switched one of the two components, the I or the B, it reverses direction. You just can't simply switch the outside connections because that switches both connections. I'll show you the same thing on the DC application. So I'll switch back to DC. The polarity was counterclockwise when we had that. So we'll energize, and it went counterclockwise again. And so in this case, you can't be switching the polarity, since it switches both the current and the field. You have to switch internally in the field, and then you get the other direction. So both setups can be switched really the same way, right? But you've got to switch the one of the two if you switch the polarity in order for it to reverse. So that's the basic operation. We'll take some torque speed data. Now we're going to start the torque speed data connected to the dynamometer, and that's because at no load the motor speeds up quite a bit because of the characteristic. We'll show a little picture of that. So here is the first data point for the motor. It's about 0.6 pound-force inches, a little over 3,000 RPM. I measured that. Current is 122 amps DC and 74.7 volts DC. So this is at 1 foot-pound. I took the data, it was 2,800 RPM. I want you to notice how much the speed changes with torque. I'm going to go to 2 foot-pounds. And you can hear dramatically how the series motor changes speed, much more than the shunt motor. So I want to give you the sense of the speed change on the series motor. These are the data points I'm going to take. So I went up to 2, 3, 4, 5, and then I finished off around 6 foot-pound inches. I'm sorry, a little more than that. 7, 8, I guess I went to about 9. But the series motor starts to slow down pretty dramatically. I went up to about 4 amps worth of current, and the speed dropped from around 3,000 to around 1,000 RPM, which you will see in the data. That's fairly typical on a series motor. Now what I'm going to do is I'm going to undo the series motor from the dynamometer to get the zero torque position, and you'll see how fast it speeds up at no load. So I have disconnected the dynamometer. So this is zero torque, only the bearings and the windage, we say, on the motor. I expect this series motor to run over 4,000 RPM, which should get pretty noisy. So we'll see what we get. So it looks like I got up to around just over 4120 RPM. So that's pretty fast motor. So I was going to show you, I told you the series motor is basically your appliance motor. Here's an old blender I happen to have. Right here I'm measuring the voltage. I'm going to turn it on. I'll turn it on low first. I'll show you how they do the variable speed on here. But this one, here's low speed, and you'll see the voltage. About 50 volts RMS. I can go up a little higher. You can hear it speeding up a little bit. This unit also has a high speed. So when I switch to high, the voltage jumps up, and then the max speed is for full voltage. So that's how series motors are used in appliances for variable speed. Of course, speed is primarily dependent on the load, because that's what determines the torque that's being developed. So we'll open up this blender and I'll show you the insides of it. So inside the blender we have the AC power cord coming in, and then the motor's in the middle there. You'll see the two connections to the motor, one on this side, one on this side. I was going to crack open this motor casing, but you can't actually get to that very easily because it's attached on the other end to the blender part. But I'll show you a picture of that with an image. Up here we have the control buttons here, so these are controlling the speed. And so this is a multi-tapped motor, meaning that we bring different wires out on different parts of the winding. So if we don't energize the full winding, then it's a lower speed.